All right. So let us resume where we left last time. So last time, remember, we went through least squares and started to look at the fundamental subspaces. In particular, we managed to look at two fundamental subspaces, null space and the row space, right? Null space and the row space. And we understood null space is a space of all vectors which the matrix maps to 0. A row space is the orthogonal complement of the null space. Okay? We also saw projectors onto those subspaces. So, for example, a projector onto the null space looks like this. Projector onto the row space can look like this, right? Orthogonal projectors. We also saw that you can use projectors to identify if the vector lies in the orthogonal complement. Like, for example, here, checking that the projection is equal to 0, we understand that onto the null space. We understand that the whole vector lies in the row space. Okay. So those were the kind of things we were looking at. Now, what was left is two more subspaces and then SVD. So that is the plan for today. Two more subspaces and then SVD. As usual, stop me anytime and ask questions. That is critically important. And it's going to do good service for all of us if you do it. So, all right, let's begin. So we begin by considering column space. So we consider the following task. Find all linear combinations of the columns of A. Okay. So A matrix has columns. Columns of the A matrix span a linear space. That is how we say it in linear algebra. Or we can say the linear combinations form a linear space. So we can find all linear combinations of those columns as all y, such as y is given equal to a x, where x represents a coefficient, a linear coefficient that in the linear combination. Okay, so this task can be reformulated as follows. Find all elements of the column space of A, Okay, that is how we can say it. So column space of A is a set of all outputs of the matrix A, or of the operator A, if you want, for all possible inputs. So you can input something like multiply the matrix by something, you get a vector. This vector will have to lie in the column space. Okay, good. We denote this as C of A. And in the literature, it is often called image of A. That is a typical way to describe a column space. Image of A. Right. So far, I think is quite simple. Now, you remember to get the null space, orthonormal basis in the null space. Let me just show you this again. To get orthonormal basis in the null space, we were calling null of A. And this was orthonormal basis in the null space. Okay. Orthonormal basis in the null space. Here, we, to get orthonormal basis in the column space, we perform what is called orthonormalization. Sounds like a best word to pronounce first thing in the morning. Orthonormalization. And yeah, interesting that we have a word for it. And hence the operation is called orth. Now, why don't we call it call, something like column space call or something? Well, the reason is that I mean, I'm not sure how the history goes exactly, but it's a time before fundamental subspaces were thrown around just like in algebra, the way we do it in this class. We had tasks that required to compute what we call to orthogonalize the matrix, basically, perform orthonormalization of a matrix, which is essentially just that: find a orthonormal basis in the image of the matrix, so in the column space of a matrix. And that was done by Gram-Schmidt procedure. If you're going to do it by hand, that is quite easy to do. I mean, as in, it's just a procedure, you can do it. Numerically, I'm not sure if Gram-Schmidt procedure is being used very widely, but yeah, it's a possible thing you can do, Gram-Schmidt procedure. In a lot of textbooks, it is still described, even in the suggested readings for this class. I think it will be described. It's just basically a way to do one by one, construct a orthonormal basis based on the matrix. Okay, good. Now that is why we have a strange terminology, orth, instead of something like call, right? Because orthonormalization was done using Gram-Schmidt procedure, and it was called this way. Now, if you open orth, this function in MATLAB, what you would find is, as far as I remember, but I'm pretty sure it's correct, you would find SVD being called inside, and then this SVD will then be used to get out the orth, the orthonormal basis in the column space. So ultimately, you just do SVD, which is interesting because if you look at all the textbooks where they describe how to get SVD, then often enough SVD will be described in terms of Gram-Schmidt procedure. So often enough, in all the textbooks, Gram-Schmidt procedure will be described as a step towards making SVD. So there is a chicken and egg situation a little bit here. But of course, in each particular case, you can just open the code and see how things are done, if it is open source at least. All right. So all I want to say is there are two algorithms here. SVD-based orth, Gram-Schmidt-based orth, and they are connected, especially historically. Like, if you're going to look at the textbooks, you will see connections. All right, but for us as users, this is just we call it and we're happy. Okay, and the null space, the previous function, is also done based on SVD. We'll soon see how both of those work. Okay. Now, let us consider the following task. Let us consider the following task. We'll consider relations between the column space and the null space here. So let A be a square matrix, which maps some linear space X, Rn, to a linear space Y, Rn. So the linear spaces have the same exact dimensions. You can think of it as a single linear space mapping onto itself. I denote them separately just to make a point clearer. So it's a square matrix, maps X to Y. Okay. Let's say A has a non-trivial null space. Non-trivial null space. What does non-trivial mean in this context? Non-trivial means, when we talk about linear algebra, non-trivial means it has more than one element. Linear space will always have one element at least, and that is 0. You cannot come up with a linear space which would be empty. You cannot come up with I mean, maybe you can, I don't know. But usually, like linear spaces, they all go through the origin. And if the linear space is zero-dimensional, it has one element, and that is 0, right? But often enough, what we care about is linear spaces that have at least one dimension or more. And that's what we call non-trivial linear spaces. So linear spaces that more than one element, have more than one element. We don't often see empty linear spaces. So that is why we use this kind of strange terminology. Instead of saying, in set theory, we would have said non-empty set. In linear spaces, we say non-trivial space, because 0 is usually always in any linear space that we can come up with. All right, so let's say it has non-trivial null space, means that the null space has at least one dimension. Okay, it follows that there are multiple unique inputs to this matrix that are mapped to the same output. So multiple inputs would be mapped to the same output. How can we prove that? How can we prove that? Well, here's an output, and here's an input that is mapped to it. Let's imagine, define XR as lying in the row space of matrix A. Okay, so XR lies in the row space of matrix A. Let's define XN as lying in the null space of matrix A. Well, if that is the case, then what we can do is, if this input produces Y, output Y, then this input will also produce output Y. How can we say it? How can we prove it? Well, pretty easy, because A times XN gives you 0 by the definition of what null space is. Okay. Hope this one is clear. Okay.
Yes, it's clear.
Okay. Right. So we have multiple inputs. They're different from each other. And why they're different? Because you get different XN, the same XR, and you get a different vector. But they all get the same output. So in fact, let's say null space has k dimensions. Let's say it has k dimensions. This situation implies that k-dimensional subspace of xn, of x, is mapped to a single element of y. So x is y, is an element of this linear space, right? Okay. Y is an element of this linear space. X is an element of this linear space. So a single element, a whole k-dimensional subset of X. Okay, so this whole subset of X will be mapped to a single element in the Y. Okay. Now that's what happens, because you can smoothly vary X along all null space and without changing Y at all. Okay, so this implies that in the column space of A, each element would correspond to the whole k-dimensional subset of X. And that means that the column space of A cannot be more than n minus k dimensional. Cannot be more than a minus k dimensions. Why? Well, because if it had more dimensions, it would mean, let's say it had like n minus k plus 1 dimension. And each of those dimensions maps k-dimensional subset of X onto it. Well, a minus k plus 1 plus k gives you n plus 1. So like X doesn't have enough elements basically to support this. So you won't be able to get more than this number of unique outputs of A, because the number of unique inputs is limited. So that is the situation. In general, you can even say it simpler. You can say that the row space of A has n minus k dimensions, since row space is orthogonal complement of the null space. So row space has n minus k elements, and each element of the row space maps to one and only one element in the column space, right? And no two elements of the row space map to the same element in the row space maps to the same element in the column space. That is basically something you can prove pretty easily. So if x1 and x2 are in the row space, let's just say it like this: x2 in row space, then we can prove that they cannot map to the same element in the column space, right? Let's assume that they do. So let's say this is how we can prove by contradiction, right? Assume that they do map to the same element. This implies the following. This implies that A times x2 minus x1 is equal to 0, which implies that the difference lies in the null space. And this, do you see what have you seen why I was writing it? Zoom sometimes shows you in between the results of typing.
No, we can see everything.
Only now, or while I was writing?
While you were typing.
Okay, good. Sorry, sometimes it is quite awkward when you talk for a while and no one sees what you are talking about. All right, so good. So this implies that the difference between x2 and x1 would have to lie in the null space, and this contradicts the idea of x1 and x2 being in the row space. If two elements are in the linear subspace, their linear combination also is in the linear space. You cannot have two elements in the row space producing an element in the null space. So this is a contradiction, and we prove by contradiction that no two elements in the row space can produce the same element in the column space. That is just that is what we were talking about earlier when we said that the row space is a space of unique, unique solutions. Basically, it's like unique elements that produce unique outputs. Okay, good. Smallest norm too. Good. So that is another way how you can prove that the column space of A would have to be, in this case, n minus k dimensional. So if you know dimension of the null space, you automatically know dimensions of the row space and column space. And left null space too, because if column space is the last one that we haven't talked about yet, if the column space is n minus k dimensional, its orthogonal complement is going to be k dimensional. So all spaces, their dimensionality are related. I think that's what we call a fundamental theorem of algebra, where we say dimensionality of the space in which my matrix operates is equal to the sum of the dimensionality of the image of the matrix and the kernel of the matrix, something like this. So very fancy, but you can see not the most difficult theorem. Okay, the name is very impressive, so and probably the consequences are as well. All right. So there is a relation between dimensionalities of those subspaces, and that's very important. If you forget those relations, just think about it for a second, you'll figure it out. That is one of those things that you can figure out on the fly. Okay. Now, let us move on. Let us quickly consider how we can project onto the column space. So let's say we have vector y in a matrix A, and we want to find a projection of y onto the column space. So this YC is a projection of y onto the column space. Okay. So since YC lies in the column space, we can always find such x that ax equals to yc. This statement, because it is kind of like, it doesn't sound very dramatic, it is very easy to just not even pay attention to what I just said, right? It just sounds as if it is like, you know, when we speak, we do a lot of meaningless statements, right? And we automatically filter them out. This is one of those. You can filter them out, but it is not something you should filter out. So let me just bring it to your attention for a second. Since yc lies in the column space, it is possible to find such x that ax will be equal to yc. I'm not saying that it is possible to write this expression and then solve it with the smallest residual or something. No, I'm saying that it will have zero residual. So it will be possible to find such x, then this would hold. So it is not a system of equations which can or cannot have a solution. This will have to have a solution, and you know, unique solution at that, right? I mean, up to the null space, right? At least zero residual solution. And if you want the smallest norm solution, you will always be able to find it. All right. So we can always find such x that ax will be equal to yc, because yc lies in the column space. That is the fact. So the problem is to minimize the difference between yc and y, since we are trying to find the projection of y onto the column space, right? And yc, this projection, is can be written as a times x, right? Since it is lies in the column space. So suddenly the problem becomes minimize the difference between ax and y. Ax is you know, this element of the column space. Y is our original vector, and we already solved it in the beginning of the previous lecture. This is just a least squares problem. Now this is a least residual problem, least squares problem of finding the smallest residual, smallest norm solution. And we know how to solve it. We solve it using pseudo inverse. We solve it writing x equal to a pseudo inverse y. Okay, and that's how we find x. But we know that yc is equal to ax. So in fact, yc would be equals to a times a pseudo inverse y. Okay. So what we found is that projection of y onto the column space is a pseudo inverse y. And we already saw it. Remember, that was what we saw in the when we discussed how to compute residual. I will just quickly show you this one. Oh, I'm not going to spend too much time, but I will just quickly show you. See, a pseudo inverse y is a projection of y onto the column space of A. And what is this thing? Well, it is this element, which is the closest ax can get to y. So the closest element of the column space to y. And remember, the closest element of the linear subspace to a vector is a projection of this vector onto this space. It is orthogonal projection. All right. So everything starts to fall in together. Good. Good, good. So this is a projection, and that is the formula. Remember that this guy here, pseudo inverse, is in practice computed based on SVD decomposition. So, and this guy here is also calling SVD in practice. It calls SVD. So in terms of computational cost, this operation is roughly equivalent to this operation. I mean, depends a little bit on what's going on there. This might be more costly because it has matrix multiplications additionally, and those can be quite large. But ultimately, and there is, since you have two matrix multiplications, it gets even more cost. But ultimately, this is similar in terms of computational cost to the previous one. So finding projection this way is not going to be much worse than, for example, finding projection, the same projection this way. So YC equals to C. Now, for some reason, I don't think. YC equals to C transpose. Transpose, when I type, I will always use the what they call it, apostrophe times Y. So this is also what I just typed here, is also a way to project. But this is not going to be computationally much better than this. It can be a little bit better, especially if you make this computation step by step, like you first compute this, then you compute this, then you can save some computations, right? But there is no overwhelming advantage over doing it this way over doing it this way. So, because both use SVD. Okay. But now you see where we get our projector form from. We saw this quite a few times. If you remember, we saw this before, not only in the least squares, but also we saw it here. Here, right? And you could ask me, where did we get it from? Where did we get this from? Well, I just showed you. So the derivation for this formula, that is how we got it. We do it via least squares. Okay. Right. And this formula is, of course, the same formula, but just different matrix substituted there. So everything falls in together. Now we see connections. How to get this formula? This is how. And it is the third time we encountered. All right. Now let's move to the other projector. Another projector is a little different. Now we'll consider projector of the onto the row space. Onto the row space. Given a vector X in a matrix A, let us find projector of X onto the row space of A. The projection of X into the row space of A. And that projection will be XR, which is equal to A trans inverse A times X. See, the difference here is that A pseudo inverse sits in between. So normally you would expect it here for a column space, but for the row space it sits here. Okay, that is the difference, and easy to remember, I think. For the row space it sits here, for the column space it sits here. How you can reason about it? How do you find like justify this? Well, I'm not going to give you a derivation. I'm just going to give you justification, as in like some intuition about it. First, this multiplication gives us output of AX. Okay. So we just plug in X into A, and we get the output. Oh, Y, some kind of Y. Then with this step here, we find the smallest norm vector that produces the same exact output. Okay. So this is what we do. Basically, we find output, and then we find the smallest possible vector that produces the same output. Now, this vector that produces the same exact output would have to have the same row space projection. So the row space component of this vector here would have to be the same one as the row space component of this vector. Why? Because they produce the same output. AX produces Y, and this guy would have to produce Y. Right? Why does it have to produce Y? Because AX lies in the column space, And when you apply pseudo inverse to a column space vector, you get exact solution, zero residual solution. Okay, good. Now, so the row space component will be the same for both. At the same time, it will be the least norm vector. It would, in fact, lie in the row space. So this guy not only would have the exact same row space component, it will entirely lie in the row space. It wouldn't have a null space component. Why? Well, we can argue just that if it had a null space component, it wouldn't be least norm, because you can always delete the null space component, the vector will become shorter. And that is how, since, least squares gives you the smallest norm solution, it couldn't have a null space component. That is one way to prove it. Another way is to just observe that this pinf, its output is a row space. Its output lies in the row space. And we will prove it in just a couple of slides. Yeah, its output is the row space, so it cannot even physically produce anything but the row space vectors. Like this matrix cannot output anything but row space vectors. That is quite neat, but that is what it does. So since we proved that this guy has the same row space projection as this guy, and it also lies entirely in the row space, that means that it is a row space projection of X. Okay. So this guy, remember, we claim that it can only produce row space vectors. One simple way to prove it is to go all the way back to a definition of this vector, which is, I believe, here. Yeah. Well, okay. We'll try to avoid doing crazy things because we'll have to reason about this matrix. Right. We'll prove it via SVD. We'll prove it via SVD a little later. Okay. So now we have two projectors. This form of a projector, this is a row space projector. And we have this form of projector, which is a column space projector. Important to remember, not very difficult to work with. Okay, good. Now we can move to the last subspace, which we haven't studied yet. That is left null space. So left null space is a space which is orthogonal complement of the column space. So we have column space, its orthogonal complement is a left null. Okay. So space of all vectors y orthogonal to the columns of A is called left null space. And this can be written as y transpose A is equal to 0. Okay. So all y's such that y transpose A is equal to 0, those constitute left null space. You can think of it as vectors that cannot be produced by operator A, but not only they cannot be produced by operator A, but the closest element to them that A can produce would be 0. So that is another way to put it. Okay. Now notice that this definition can be transposed. So we can transpose it. Transpose gives us A transpose Y equal to 0. Interesting. A transpose Y equals to 0. So that means that left null space is equivalent to the null space of A transposed. It's quite elegant proof. A transpose Y. This is equal to 0. We're just talking about null space now of transpose matrix. And it is exactly the same as left null space of the original matrix. So we see connections. There are connections between fundamental subspaces for transposed of a matrix and for the matrix. And if you think about it, for a second. It sounds completely bizarre. As in, you can just believe me, of course, and that might be a good idea in this case. But you can also doubt me, right? You can say, how can it possibly be that you have columns and you put them sideways? So columns, you don't even know how they're arranged, right? Let's say you have 4 columns, right? Like how I have 4 fingers showing here. Let's say I shift them around, right? I rotate them somehow. Column space is not going to change in any way, right? Row space is not going to change in any way. Null space is not going to change in any way, right? So you can shift those columns around as much as you want. It shouldn't interfere with anything about the matrix. How can it possibly be that we can put them sideways and produce a matrix which would have anything to do, whose columns would have anything to do with our columns? Bizarre. Fact of the matter is, that's how it works. And for example, null space of the transpose matrix we just proved is going to be left null space of our original matrix. All 4 of them will be connected. So very interesting and very important to remember, because this is something that people expect you to know. You will see what I mean maybe you would see what I mean just now. Let me just see. Okay, let me first talk about projectors, and then we'll explain what I mean. So we want to project vector y onto the left null space of A. Okay. So if we want to project it, what we can do is first we project y onto the column space of A, and then subtract the result from y. So this is how. So we just project y onto the column space, and then the result we subtract from y. So we get this expression here. And this would lie in the left null space. If C is orthonormal basis in the column space of A, if C is orthonormal basis in the column space of A, we can find projection this way. Again, project y onto the column space, subtract from y. That's what we get. Here you can ask me, why don't we call something like L equal to left null of A in MATLAB if we have such a function, and then say YL equals to L transposed times Y. This would definitely give us, if L is the orthonormal basis in the left null space, this would give us a projection onto the left null space. So why not do it this way? Right? Why not do it this way? Well, you would be surprised to know that MATLAB does not have this function. Doesn't have a function like that. Doesn't have a left null function. Same as you cannot call something like R equal to a row of A, like a row space, let's see. Yeah, row. Doesn't have a function row. It has null, it has orth. So we have null and orth, but we don't have these guys. Right? For some reason, we only have null and Python too. It's not just MATLAB, of course. So what's going on here? What's going on here? Well, the reason why they don't have functions like row and left null is because you can compute. I mean, I'm not defending MATLAB or Python. I think they should have those functions, but maybe they're trying to force you to learn algebra. Maybe that's why. I don't know. Ultimately, all of those functions are wasteful in many ways because they compute SVD and then they discard half of them. But anyway, what is left null? Well, how to compute left null? Well, if you want left basis is left null, you just compute it as null space of A transposed. That's how you compute basis in the left null. How do you compute row space basis? Well, you just do orth of A transpose. Interesting. How do I know that this works? We'll prove it in just a few slides. We'll prove it very soon. But that is how you do it. So the reason why they don't have row and left null is because you can just compute it this way. That's what MATLAB expects you to do, and Python too. Okay. Is it clear for now? Do we have questions?
It's clear, Professor.
Okay. Thank you. Okay. Then let me move on. Now we start the last part of today's lecture, SVD. So all of what we have been doing so far is completely based on SVD. Pinf is SVD, null SVD, orth SVD. We didn't do rank. Rank is also SVD. So when we were saying dimensionality of the linear subspace, let's say what is the size of the column space? You can find it by calling rank of A. That would also be SVD. So all of it is SVD. Let's discuss SVD, but we'll discuss it in terms of subspaces. Typically, in the textbook, what you would find is that SVD of a matrix is something like this: U times sigma times V transposed is equal to A. Right? This is a typical way to discuss SVD. I will discuss SVD in a slightly different way. I'm going to discuss it as instead of U, I'm going to write it as CL. Instead of V transposed, I'm going to write it as Rn transposed. Instead of sigma, I'm going to write it as a sigma 0, 0, 0, 0. Okay. Let us now understand what those are. So this C is a column space basis, orthonormal basis in the column space. This L is orthonormal basis in the left null space. This R is the orthonormal basis in the row space. This N is orthonormal basis in the null space. And they all are in the SVD decomposition. Is that surprising? Did you study this part before? Did you study this connection between SVD and fundamental subspaces in your algebra course? Also, I assume from your silence, no one did. Okay, so at least first time we find something that no one studied before, I think. Great. Okay. Now, this is how SVD looks like. Now, of course, there are infinitely many ways to define a basis in the null space, in the row space, etc. So it shouldn't be actually very surprising. But yeah, how can you kind of like understand that R is, for example, row space and N is, for example, null space? Well, just look what multiplies. N is going to multiply this 0. Okay, it's going to disappear. It's not going to have any effect whatsoever on anything. So N, columns of N, are not going to have any effect. And that is how you know It is a null space element. Okay. Row, on the other hand, will multiply sigma. So sigma is a full rank matrix. I didn't tell you about sigma yet. Sigma is a diagonal matrix of singular values. They are positive and they are sorted from the biggest to the smallest on the diagonal. Okay. So R is going to multiply those singular values. Okay. Now, how do you know what is column space and what is null space? Well, sigma is going to multiply C here. So it's going to produce an output. Okay, so C will produce an output. Now, this 0 will multiply, with this 0 too, will multiply this L. So this L is not going to produce any output whatsoever because it will multiply by 0 on the left. So this is left null space. It's what's not going to be produced. Yep. So even if you studied SVD in this way, you could have figured it out without, without any additional difficulties, right? It just follows from the fact that those are orthonormal bases, that the columns are mutually orthogonal, and from those zeros, that's all you need to know. Okay. Now, let us move on and see what we can do. First of all, before we move on, let me just mention that this whole thing can be simplified. We can multiply it all together. Like we multiply, for example, this by this and by this, right? Then the result we multiply by this, and what we get is this expression here. What we get is this expression here. So it will be row space transposed times sigma times C. That is what the matrix is going to be like. This, I think, is what they usually call economical SVD decomposition. I haven't tested, but I think SVD con is what is going to produce you this decomposition without those zeros and without left null space and null space. Okay. Good. Now we know what it looks like in terms of subspaces. Now let us move on. So the rank of the matrix is computed as the size of sigma. Okay, the size of sigma. Sigma is a full rank matrix, but note that in order to find the cutoff, so what is sigma and what is 0, computers use tolerance, numeric tolerance. And if your tolerance is coarse, sigma is going to be smaller. If the tolerance is higher, the sigma is going to be bigger. And you don't always want higher tolerance. Often enough, you want coarse tolerance. You just need to be sure that you are consistent. So you cannot, for example, find rank using one tolerance, find SVD using another tolerance, find null space using the third tolerance. You have to use the same tolerance every time. Otherwise, your results will be wrong. And here is the first time when I have to say it. But in MATLAB or Python, not all functions have built-in ability to pass tolerance. In MATLAB, for example, one of those functions, I'm not sure which, I think maybe null, doesn't have ability to pass tolerance. So what happens is you want to compute null with a specific tolerance, but you cannot. You'll get machine tolerance. Machine tolerance is, in MATLAB, you can see how it's computed. It depends on the size of the matrix. Just type open null and you'll see how it's computed. So if you cannot pass it, you are stuck with machine tolerance. And that means if you computed pinf, I think, I don't know if it allows tolerance. But if you compute your rank using machine, your tolerance, like the tolerance that you like, and now, for example, using a different tolerance, they're not going to be consistent size. The size is going to be inconsistent. So you're going to have errors. And this is quite significant. So when you do anything with SVD, null space, projectors, PINF, think about tolerance. Just think about it. If you don't see any problems, go on. If you see a problem, stop and solve the problem. Okay. In my practice, I have had problems with inconsistent tolerance. And my solution was always to write my own software, which would call, of course, built-in SVD functions, but it would not use like null, pinf, etc. Instead, I would do everything by hand with the tolerance being the same everywhere, right? By hand, I mean, I would just do SVD once and make sure the tolerance everywhere is the same. You can have all kinds of other ways to do it. On the only point I'm trying to make is that you cannot just brush it off as in like whatever hyperparameter, who cares? No, important. Okay. All right. Now pseudo inverse. How to compute a pseudo inverse? Well, pseudo inverse is computed this way. It's computed this way. Can someone tell me why? Someone tell me why it's computed this way. Suggestions, guesses. Let me make a suggestion. So remember that A is equal to C sigma R transpose. Now, nice thing about this expression is that you can try to invert it. You can try to invert it. So you can say in inverse of A. See, I mean, you cannot invert it like analytically, but because those matrices are not square, right? But let me put it this way. So what you can do is, let me copy this. What you can do is to try to start to at least get it back to 0. So for example, you can multiply both sides by R, right? By R. Multiply both sides by R. This way, let me move it all up. This way, this expression here would actually lose this component, right? That's what it would become. Because R is orthonormal, so it times its own transpose will give you identity. Then you can multiply it by C inverse. Sigma is a full rank matrix, so you can always multiply by sigma inverse. You don't have sigma anymore, but you have sigma inverse. I would denote it as maybe I sigma. Make more space. Okay. Now, next, what you can do is multiply everything by C transpose. And you will guess what happens next, right? C transpose times C is identity, so we have identity. And notice what we got here, this matrix, is a right annihilator. Well, I don't know, annihilator sounds like fancy. Right inverse of A. So this guy that we got makes A into identity on the right. This is what we have here. This is how we got to this expression. But what about this guy? Well, this is the same expression, just written in a fancy notation, because those zeros will delete n and will delete L transposed anyway. So in practice, this is just a fancy way to write the same thing. 23 doesn't have computational aspect to those additional elements. 24 is exactly the same as 23. Okay. All right. All right. Do we have any questions? So we found how pinf looks. Now notice that with this, we automatically prove that pinf lies in the row space. Why? Well, because it is defined as something multiplying R multiplied by something. Since R is a row space, no matter what you multiply it by, it will still produce a row space vector. So the columns of R cannot produce anything but row space vectors, because they are bases in the row space. So that's how we can prove it. Pinf is defined this way, and we get what we get. At this point, you can ask me, is this pinf the same as pinf of A, which we defined earlier, which was A times transpose times A inverse, right? Times A transposability. That is the definition of universe we got before. And I'm not going to comment on that. You can try to study the relations between those two and whether or not they produce the exact same result. Okay. So can they produce different result? Of course, theoretically speaking. You know, we didn't prove that they don't. But you know, you have to, if you want to show that they're different, you have to show it. If you want to show that they're the same, you have to show it. In practice, pinf that you actually call in MATLAB is never going to compute this guy. It is always going to compute this guy. Okay. So I will leave it to you to figure out the difference between those two. And notice here we were talking about how this guy can sometimes drop a rank, and not have exact inverse. Here we don't have such problem, right? As long as it has the SVD decomposition, everything is fine. Okay. Okay. So this is another aspect. And finally, of course, this was always a little bit nonsensical, this definition, because this thing here. How do you compute exact inverse of a matrix? You don't expect the matrix to actually perform like adjoint, compute like adjoints or like, you know, minors, etc. All those things, or like, you know, whatever you would use, like the definition of what inverse is. Even determinant of a big enough matrix is very costly to compute. So you don't actually expect that to be done, you know, exactly. MATLAB tells you not to use it, exact inverse. So this definition was always suspicious. Okay, okay. Any questions about that? Okay, no questions. This is something you know need to internalize, like those things. Is just important for you. Like it's not necessary for the exam. Well, might be, but I'm not saying that I'm not going to ask this on the exam. I might ask this, but mostly it is just important for your understanding of algebra, those things. Okay, Now, a few interesting connections about transpose. Let's find SVD of A transposed. So same as any matrix, it has some C, L here, some sigma here, zeros here, R and N here. So this is just generic SVD, same as before. Now let us transpose this matrix to get a region. Transpose of a diagonal is the same as a, I mean, it doesn't do anything, right? You flip the diagonal, it doesn't change. So what we have when we transpose it is that these guys, they go here, okay? And these guys, they would go here. Because you transpose, so you first you kind of shift them around, and then you like the one that was standing would fly, the one that was lying would stand. So that's the idea. I mean, if you feel uncomfortable with it, just look at the transposition rules for like product of two matrices. You can do it like, you know, one by one, and that's it. I mean, AB transpose is equal to B transpose times A transpose, right? Okay, good. So that is why here we have R, R went here and went here, and they lost their transposes. And C and L acquired transposes, and they went to the left, but to the right side. Now, notice that this is the original matrix, and we know that here for the original matrix, this is the column space. Okay, so for the original matrix, this is a column space, but it is a row space of the transpose matrix. They're exactly the same, but this is the row space of the transpose matrix. This is a null space for the original matrix, but it is the same as left null for the original matrix. But it is the same as the null of the transposed matrix. Okay. This is a row space for the original matrix, but it is exactly the same as a column space of the transposed matrix. Finally, this is the null space of the original matrix, exactly the same as the left null of the transposed. So this is how we can prove all of those relations almost effortlessly. You just write this out, transpose it, and find the connections. But it's also easier from the names: null and left null, column and row. Easy. Okay, so this is how you prove those things. That's how you prove those things. Good. Now, finally, let us prove some equivalences about the projectors. So I was saying that this guy is a projector onto the column space. And this is also a projector onto the column space. Let us prove that they're the same. So we get two expressions for A. So this is A. So let me do it this way. This is A. And this is inf of A. Notice A is C sigma R transpose. Pinf of A is R sigma inverse C transpose. Right? So what do we do? First, we recognize that this here, let me use red. This here will go to 0. Why? Oh, to 1, because R transpose R is 1. So next, we don't have it anymore, but we still have something that goes to 1. Sigma times sigma inverse goes to 1. That's how we prove that A pseudo inverse is equal to C transposed. Great. Great. By the way, since C is not uniquely defined. So you can have multiple ways to define a column space of C, right? I would ask you to think about the following. Is A pseudo-inverse uniquely defined? That is the first thing you can think about. And second is this whole thing uniquely defined? Okay, just something to think about. Yeah. I mean, I guess just in case, so I won't create a huge headache for you. There's like algorithmically speaking, all of those, this problem can be solved very easily. Yeah. So the way it can be solved is this: we said that C is diagonal matrix of singular values, and they are sorted. They're sorted in the decreasing order. Since they are sorted in the decreasing order, actually they are in SVD decomposition, they are uniquely defined. So for one matrix, will get one and only one C. Okay, same as all of those. Like this is also uniquely defined. Those, not sure. About N and L, not sure. But C and R, you'll always get exactly the same ones because of this property. But let's say you find a different null column space basis. What's that? So it's just something for you to think about. What's that? Okay, good. Good. Now another question. We have A pseudo-inverse A. We said that it is a row space projector. A row space projector. Okay. And this is also a row space projector, right? Like R transpose is a project onto the linear space as long as R is a basis in this linear space. So they should be equivalent. Let's prove it. We start by noticing that this is the A, right? A pseudo-inverse is this. Then we note that this goes away because C transpose C is identity. So it goes away. Sigma inverse sigma is identity, so it goes away. So what we're left with is a solution. A transpose A is equal to R transpose. It's very nice. It's one of those cases when the proof is very satisfying to look. It's kind of like Tetris. They go away one by one. All right, good. Now, let us, any questions about it? Okay, let us look at something more challenging. I promise we're not going to do too much here, but just a little bit. We will prove that P, we will denote it as A transpose, so projector onto the column space, P. We will prove that it has the following property. P times P is equal to P. So you can project something twice, it will be the same as projecting it once. So P times P is equal to P. Okay. That is a property of orthogonal projectors only, not for any projectors, only for orthogonal ones. Okay, let us work on the proof. First, let us identify, let us express it. We'll express it as A inverse, A inverse. Here are A's, one A, another A. Here is A inverse, one, another. So one, another. Okay. Now we can get rid of this because it is identity. This is identity. This is identity. Okay. What is left is sigma, 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 sigma. This is identity again. This is identity again. And finally, we are left with this, which is C transpose, which is the same we proved before as A pseudo inverse. And that is what we tried to prove. We can do exactly the same thing for projector, which is A pseudo inverse A. That is a little bit redundant because you know, what is the difference of how you exactly define a projector, I guess, right? But we can prove it. We'll get this guy, I have to be equal to this guy. And you can imagine already that, you know, the same thing, patterns that created those things will create the same patterns here. And you would end up with a row, like R transposed, and you would prove it's this way. Okay, good. Any questions?
I have a question.
Yes, go.
I see that, yeah, the math makes sense over here in this example, but may I ask about the meaning of having this property of projecting twice? What does it like actually mean?
So let's say you have the following problem. Let's say y is equal to m times p of x minus let's say m times p times x. Like that is let's say something that you found in your problem. You know that p is a projector, right? So from this property, if you can identify that this guy here and this guy here are exactly the same, you will prove instantly that y is equal to 0. Okay. If you cannot identify it, well, you're going to have some difficulties. For example, if you were to just continue this without knowing the property, what you would get is probably something like this, right? You'll get, you'll start to get things out of the brackets. The only thing you can get out of the brackets is first like x, p times x, right? So you'll get something like brackets this minus m, right? Like this, correct? And then you can even do it like this. Right? You can get m out of the brackets too. I guess here, the nice thing is that you can still save yourself. Here you can save yourself. And the reason you can save yourself here is because you can also observe that this is a projector. Sorry, let me do it this way. This is a projector onto the orthogonal complement of the image of this projector. But that is not as easy to see. But this is a projector onto the orthogonal complement of the space to which this projects. So they have to annihilate into 0. That is also something you can see. But basically, what I'm trying to say is that if looking at this, you can just instantly say, okay, this is the same as p, or you can say, okay, this is the same as p times p. Great. Is going to make it much simpler for you to do derivations for your proofs and you know, algorithms. That is the whole point of this property, just to make it simpler for you to derive.
I see. Thank you very much.
No, thank you for the question. It's a good question. It's one of those things which you don't appreciate until you see, but that is extremely extremely nice. Also, what is also nice is that in those cases, often enough, what you can do is just directly, like you have p, you can replace it with like C transpose, for example, or something else, and your proofs will go forward. So sometimes it is nice to be able to replace those things with something else. And this mastery, you'll get it from practicing all those formulas basically, because you just have to keep in mind all the possibilities. And that is all. Like you can have to keep in mind that this and this is the same. You see both of them in the same context, you can replace it. And that is going to keep you moving forward in the derivations. All right. All right. By the way, the fact that this annihilates, like that this thing would have to be equal to 0 is an interesting factor. And it can be useful in some respect, in some formulas. Maybe that's exactly what you would want to get, and that's maybe sometimes is why you would want to have like p times p somewhere. I don't know. And again, it's not just nice, a good thing to have, a good thing to know, right? By the way, how do you know that this is orthogonal to this? Well, remember we saw it like 3 times before or more. If p is equal to a times p of a, that is a column space projector, right? Well, let's say I would call it, I don't know, f equals to I minus a p of a. That is a left null space projector. Is the orthogonal complement of this. And of course, a projector onto the column space, the columns of this projector would also be in the column space. So you multiply them by the columns of the left null space projector, and they would have to annihilate. Of course, you need to make sure that what you do is in a product, not something random. And for that, you need to maybe prove that this guy has, I mean, you need to be careful, basically, I'm trying to say. You cannot just multiply, you have to make sure that the columns are multiplying the columns as a dot product, not just some random fashion. Anyway, I don't want to go into details without having a slide. It's not easy to visualize. So, any more questions about this part? Okay. I think we're almost done. Let me see if we have anything. Yeah, last property. That is just interesting. We can try to prove that P pseudo inverse is equal to P. That is just bizarre. Like at this point, you don't even trust me, I think. And to be honest, I don't trust myself. I look at this after seeing this proof many times. I still look at it and I feel like, come on, this cannot be possible. Identity, yes, identities would have this property, but P, why? Quite interesting, quite interesting. So first, let us try to prove it. I mean, we'll just try. And if you feel uncomfortable with this, that's a good feeling. I mean, you have to be uncomfortable a little bit, always, to double check yourself when you do math. You cannot just do it without proofs. Okay, let's prove it. First, we will describe P as C times C transpose. Why can we do this? Well, there is some orthonormal space to which P projects. We will just describe P as like in this fashion. We'll have to double check that the result is the same, by the way. That is, you know, like I guess I'm skipping steps here, like with this step. But because we have to kind of like, here we sort of assume that there is only one orthogonal projector onto the space. But we assume that P is orthogonal projector. So. Okay, good. So we find the basis, orthogonal basis in the space to which P projects. And then we find P as a projector onto this space, but via this basis. Okay. That's what we do. Now, we know that P times P pseudo inverse should be equal to 0. Otherwise, it's not even a pseudo inverse. It is something else. right? So if pseudo-inverse exists, it has to have this property. Now we replace, let me just use my colors. We replace this with this. Okay. Then we multiply both sides by C transposed. So here, this guy will go away. And here we will have C transpose because of that. Next, we multiply both sides by C. So this guy will go away. And here we'll have C, right? C transpose. And what C transposed is actually just P, right? And that's how we prove that P is inverse equal to P. That can be useful quite often when you solve least squares for a system which has a projector inside the system. But you need to be extremely careful when you do those things. Like making mistakes here is much easier than finding correct formulas. So just double check, triple check. And when I say double check, you can check it on your paper by derivation, like I did here. Then you generate a huge amount of examples in Python, and you check that all of them work. And by huge amount, I mean randomly generated matrices, but also different ranks. Also try to find corner cases when something can go wrong, etc., etc. Check all of your assumptions. Like, do you assume that C is like any orthonormal basis over a specific orthonormal basis, etc. Like, check all of your assumptions and check that it works. Like those types of derivations here, I'm not even showing it to you to rememorize. I'm just trying to show you how you can attack a problem. And if it leads to correct results, great. But if it leads to contradictions, you have to study it until you resolve the contradiction. In this style of work, you cannot allow yourself to just do the derivation and hope that you did it right, test it in one example, it works, you forget about it. No, you have to like go at it until you are completely satisfied that all the proofs and checks work. Very easy to make a mistake here, right? Okay, I think that is the last one that we had. That is the last one that we had. Here is a suggestion what you can read. Quite nice textbooks by Mikhail Lavrov. I think those are like class handouts. It's just to see a different perspective. Okay. This is from some American university. I don't remember which one. The slides are always here. This time we also have an appendix. In appendix, there was a need to prove that two definitions of orthogonality are the same, right? One is that orthogonality of a vector in the subspace is the same. One was vector y whose dot product with any x and L is orthogonal to the subspace L. That is the definition of orthogonality. Another one was vector y closest vector to the linear when the closest vector to it in the linear subspace L is zero vector, then y is orthogonal. We can prove that both of those are equivalent. You can read it on your own. This is again provided mostly for you to see the style of arguments. Like we want to show that y1 implies 2, and then that 2 implies 1. You can just follow it, and that is mostly for you to just kind of exercise. You don't have to, it's okay. But yeah, this finishes our block on linear algebra. That was mostly recap, but some of it was new, as we discovered. We will use it throughout the whole course, this linear algebra, but even in itself is extremely powerful. We'll use it mostly in convex optimization, but you can use it without convex optimization to justify it. It's just good. So try to find time to practice. Try to go through the slides, see what exactly you don't understand, and practice that. Ask me questions about it throughout the whole course. At any time, we can go back and review. So I'm happy enough to do it. I hope I didn't take much longer than what we had. Did we run way out of time, or only a little bit out of time? I think only a little bit.
No, I think we are on time.
On time. Great. It's the first time when I deliver this lecture when we don't run like 30 minutes more than we have to. All right. Thank you, guys. I'm very glad we managed to get through the first most difficult, compact part of the course. Later, we'll go much slower. So I promise you, breakneck pace is almost over, pretty much over. So thank you for sticking with the program. Any questions for today?
Professor, can we get the link of the YouTube video?
Yeah, I didn't upload the video yesterday. I had to prepare for like classes, so I will upload both today. I'll send you the videos and playlist.
Sure. Thank you, Professor.
No, thank you. Any other
One
questions?
question.
Yes.
One question.
Yes.
About this SVD decomposition.
Yes.
The C and R bases are also normal bases.
Yep.
So are they uniques?
1 second. I will just quickly. My apologies. I will just quickly go back. SVD. Sorry, I managed to mess up just when you were asking. Come again. So what you were asking?
I'm asking about C and R bases. They are also normal bases.
C and R. So C is, yeah, of course. They both are orthonormal bases. C is orthonormal basis in the column space. R is orthonormal basis in the row space.
So they are unique here.
No. Same as any orthonormal basis, they you can replace them with any other orthonormal basis, which would be achieved by multiplying this basis by like how should I put it? I don't want to kind of like go into something too complicated there. So let me just show it visually to you. What I mean. Right? Imagine this is an orthonormal basis, right? Vectors are length 1 and orthonormal to each other. Now, this is another orthonormal basis. Vectors are length 1, orthogonal to each other. Same can be done in any dimensions. In this case, you notice that what we do is we rotate all those vectors. So we basically multiplying them by a rotation matrix, which itself is also orthonormal. So in higher dimensions, you would have more possibilities. For example, in 3 dimensions, you can rotate around this vector, like around this vector, right? Rotate like this. Around this vector, you can rotate like this. Around this vector, rotate like this. I guess I should have pointed to the camera, right? Like this. Okay. So you would have 3 rotations in 3-dimensional subspaces. In 4-dimensional, you would have, I don't want to lie, I think 6, but I'm not sure. It has, there are theorems that will describe to you how to do this. Okay. So it has to do with dimensionality of SO3, if of S or N groups, and so on. But all of this is nice, but fact of the matter is, since sigma is sorted, this gives much less wiggle room to what C and R can be. So some bases in those spaces can be chosen arbitrarily, but SVD will give you very particular S and R, since you cannot you cannot just shift them randomly without changing the output. And sigma is defined exactly, completely strictly. in the descending order. So that is why the output here is going to be predetermined. And the same goes for null, orth, and all other operations which are based on SVD.
Thank you.
No, thank you for the question. Any other questions? All right, then this is it for today. Thank you, guys. We'll see each other next week. Bye-bye.
Bye-bye.
Thank you. Goodbye.
Bye,
Bye-bye.
Professor. Thank you.
Thank you.